Hey, what's up? It's Miss Wesley. Excited to be back here to talk with you more about complex numbers in polar form, looking at page 14 of the polar packet. And speaking of complex numbers, let's refresh. We've got rectangular form x plus yi, right, that we've worked with before. And now we've got this equivalent form, and there's an abbreviation for it. It's r cosine theta plus I sine of theta. So in shorthand, we could just write CIS, which means the exact same thing. And the question we've been asking all unit is, okay, so what are the advantages of having these two forms of the exact same thing? We've already seen the graphing capabilities that come with a polar function that are a little more natural than trying to graph those same things rectangularly. And now, over the next few pages, we'll look at some algebraic advantages of having a complex number in polar form. So we're going to start with multiplication and division. You might be thinking, man, I would love to start with a joke. So the question is, have you heard about the rumor about the butter? And never mind, I probably shouldn't tell it because I shouldn't spread it. Underneath here, I inserted a proof just to get some background info on why these rules work the way they do, but the most important stuff we're going to jot down here are the rules and the shortcuts for products and quotients of two complex numbers. And you've got this z sub 1, which is r sub 1 cis theta sub 1, and you have the second complex number z sub 2 that has the two subscripts, r sub 2 cis theta sub 2. And if you looked over this for a second just to check it out, you'd see that you could come up with this rule on your own. You'd multiply the two r's together. That just got shifted out front in the proof. And then once you FOIL and simplify carefully the two binomials that are present, you end up getting an old friend. You get the cosine of a sum identity as a trig identity, which is the cosine of the first angle plus the second angle. And then you actually get the sine of the sum identity in another set of parentheses, the sine of the first angle plus the sine of the second angle. So that you don't have to go through this entire process every single time we try to multiply. Just use this rule. Here's the summary. If you want to multiply two complex numbers, let's take the product of the two moduli, the two radii, r sub 1 times r sub 2, and then let's take, I'll put cosine plus I sine, so cosine of something plus I sine of something. What is that something? It's not that you multiply the two angles. That number would actually come out to be too huge a lot of times. You're going to add the two angle measures together. So it's cosine of theta sub 1 plus theta sub 2 plus I sine of that same argument, the sum of the two angles. Or other times in mathematics, with logs and exponents, with those rules, multiplication and addition often go together. And I'd like to write this in shorthand too, so another way to write it, just if you're trying to go quick, r sub 1, r sub 2, so multiply the two r's we said, and then cis, the sum of the two angles, theta sub 1 plus theta sub 2. Okay. And I think this might help you guess what the very next rule is going to be. What if we wanted to divide two complex numbers? A very similar proof would lead you to the conclusion that you can divide the two radii, so r sub 1 over r sub 2, top over bottom, and then cosine of, what do you think the argument's going to be? So with multiplication, we added the two angles. With division, let's reverse that. We're going to subtract the two angles. So the top angle, theta sub 1, minus the bottom angle measure, theta sub 2, plus I sine of the exact same angle, theta sub 1 minus theta sub 2. And there's your rule. And you're going to see multiplying, dividing complex numbers in polar form is very convenient. It does go pretty quick. Shorthand, r sub 1 over r sub 2 when you're dividing. And then let's subtract, like we said, the two angles, the cis theta sub 1 minus theta sub 2. All right, let's put it into practice. Let's start with number 5. Find the product. We'll do this all in polar form and then leave our final answer in rectangular form. All right, well, what does the rule say? First, I'm supposed to multiply the two r's. So the 3 and the 2, new radius is going to be 3 times 2, so I get a 6 out front. Cosine plus I sine, I'm going to be lazy and just write cis there for starters, and then I have to see what I'm going to do with the two angles. Well, the rule says when you multiply two complex numbers, you add the two angles. So pi over 4 plus another 3 pi over 4. And this looks like it'll come out quadrantal. 6 cis, just a regular pi, right? A quarter pi plus 3/4 pi. Here's your answer in polar form. To figure it out in rectangular form, great practice of just converting. So 6 Let's write out the whole thing. Cosine of pi, what this really means, plus I sine of pi. And we'll go to work with our exact values. So let's simplify this to get to rectangular form. Cosine of pi, right? So 6 cosine of pi, we should be over at -1, plus I sine of pi is going to be 0. So all said and done, bringing the 6 through here just gives you -6 as your rectangular answer. And that's like saying -6 plus 0i. If I were to plot it, it should be exactly where I would have imagined 6 cis pi to be. Go over an angle of pi, come out 6 units on that angle. So -6 in rectangular form. And we could do the same thing to 6 and 7. Feel free to pause the video and try 6 and 7 on your own. Just for reference, 6's answer is just going to be 10, the real number 10. And 7's answer is actually just going to be 16i. It'll just be an angle that goes right up on the y-axis. But I want to try 8 with you now. I want to skip over to this one. Try this one the same way. First, can you get me a new r value? Let's multiply the two r values that we see in these two complex numbers. So 3 times 4 gives me 12. And then abbreviation, cosine plus I sine, we got to add the two angles. So 2 pi over 3 plus pi over 6. Okay. So when all said and done, to simplify, we get the angle, well, this is like 4 pi over 6 plus another pi over 6 gives me 5 pi over 6. So if it's an angle I recognize and the problem just says to give an exact answer, that's no issue. We'll leave it as 12 cosine of that angle plus I sine of that angle. Sine of 5 pi over 6. Okay, so now for simplifying. 5 pi over 6, I want to keep in mind just what quadrant I expect to be in. So I want to be in quadrant 2, where the sine and its reciprocal are positive, but the cosine is negative. This will be 12. Well, 5 pi over 6, you're going out further than you're coming up. So we'll say 12 times negative square root of 3 over 2, your exact value for cosine of 5 pi over 6, plus I, and then the sine of 5 pi over 6 should just be a half. And we'll leave our final answer simplified with no parentheses, just in that x plus yi format. So 12 times this fraction gives you -6 square root of 3 exactly, and then plus 12 times a half, we'll say 6 times I. And there's your rectangular form answer, which also falls in quadrant 2. Let's try some dividing on the next page. Find the quotient. Okay, I see finally a problem that's written in degrees. It's been a while for this, but the rules still apply, whether you're working in degrees or radians. Divide the two r's, so 24 over 8 gives you your new modulus. And then it's cosine plus I sine. Let's subtract the two theta, so 300 minus 75, the theta that's on the bottom, gives you in degrees only 225 degrees. And this is one of our angles that has a special reference angle of 45 degrees as well. So that's your polar answer. We want to, get some more practice converting this to rectangular form and making sure that we get what? 225. We get a quadrant 3 solution where only tangent and its reciprocal are positive. Let's write it out, long format. Cosine 225 degrees plus I sine of 225 degrees, like that. 3, well, these are the exact same number, right? You're in quadrant 3 where both the cosine and the sine are negative, square root of 2 over 2. And then I'll say plus I times the same exact value, square root of 2 over 2. Okay, and bring in the 3 to the parentheses. -3 square root of 2 over 2 if we want to keep this separate. Plus, I'll just bring everything to the top here. And maybe I should have said minus. So instead of that plus, let me change it to a minus. We've got a negative value. 3i squared root of 2 divided by 2. So 2 negatives for x and y should land us where we want to be in quadrant 3. One more, this one's in radians, real quick. 2 over what? Well, we have a silent modulus out front of 1. So 2 over 1 is going to be your new r value. And then we subtract the two thetas, this time in radians. So pi over 6 minus pi over 3. To get, and I should have said cis here, right? Cosine plus I sine. So 2 cis, this difference, which is negative pi over 6. So we're thinking quadrant 4 for negative pi over 6. And we'll write that out. 2, we've got cosine negative pi over 6. We can find that in a second. Plus I sine negative pi over 6. Okay. See how that looks? You're coming out further than you're going down, and you're going in the positive direction. Cosine's positive in quadrant 4. So 2 square root of 3 over 2 plus I, and how about negative a half for the sine of it? So some exact value practice at the end. 2 comes into both parts. You land with just square root of 3 minus I. Now, instead of answering the question 11 that's printed on the page, I actually want to get rid of this one, and I wrote one or two more where if you could have your calculator handy, we could just practice the simplifying together with these. So try this new number 11. Same directions, you're either multiplying or dividing two complex numbers. I want to multiply 1/2, and I'm going to use the abbreviation notation here, cis, cosine from plus I sine, of 180 degrees. So I'll be in degree mode. Can you find the product of that and this one? 3/7 cis, I chose 350 degrees, like that. Okay, same rules apply here. We want to what? Multiply the two r's, so give that a try. Product of 1/2 and 3/7, so 3 over 14. Cosine plus I sine, I'll write cis there, and I want to add the two thetas, so 350 plus 180 gives me 530 degrees. Okay, so there's what you have for starters. You can leave this as a 530 because we're going to be using the calculator anyway. If you really want to think about a quadrant that you're in, it might be good to subtract 360 from this. Find something coterminal that'll get you the same solution. So what we just wrote is equivalent to 3/14 cis. 530 minus 360 is 170 degrees. So now I know I'm aiming for a quadrant 2 solution right before 180, where only sine and its reciprocal are positive. Well, we've got our polar form. Good practice to convert to rectangular, right? So 3/14 cosine of 170 when the whole thing's written out, plus I sine of 170. And if you run across an angle like this where you don't have its sine and cosine memorized, usually the directions are going to let you round to the nearest, I'd say, thousandth or 3 significant digits. So try it. Type this first part in, 3/14 times the cosine of 170 in degree mode. And your calculator will give you an approximation of about 0.211. Okay. Plus, now here comes the 3/14 into this part. Sine of 170 is positive. 3/14 times that gives you 0.0372 with 3 significant digits there, and then an I. Number 12 as a last problem to try for practice. I said 6, I'll write this out the long way. Cosine 5.2, notice there's no degree sign there and that's on purpose, plus I sine of that angle, 5.2. Divided by 11, another complex number, cosine, I chose 4.6, plus I sine of 4.6. Like I mentioned, it's not a mistake to not have the degree sign there. These are meant to be angles given in radians. So anything we use the calculator for help with in this problem is going to be approximated with radian mode. Start the problem the same way. Divide the two r's. So 6/11 is going to be good for your new r value. Cis, this time I'll use the shorthand, and we want to do 5.2 minus 4.6 radians to see what kind of an angle we get. So it's 6/11. Here I'll write this out. Cosine of what angle? Just a 0.6, quadrant 1 radian angle, plus I sine of that same angle, 0.6. Same deal, use the calculator. I would recommend radian mode for this one instead of degrees. You got 6/11 times the cosine of 0.6, again, approximation, nearest thousandth, 0.450. In the next spot, this is a quadrant 1 angle. Everything comes out positive here. 6/11 times the sine of 0.6, 0.308 I. And then we've got it. So multiplying, dividing, stay tuned as we get into some other cool stuff in the days to come. Have a good day.